Assalamu alaikum. All right, so today we're going to start a different kind of discussion, and we're going to see that the universe is made up of two kinds of entities. One is matter and the other is radiation. And in the pre-quantum times, it was believed that radiation is a wave-like phenomenon. And the matter has a particulate entity, that is, it is made up of particles. And this idea that all of matter that we see around us, matter is something that we can touch, see, feel. The matter that we see around us has some graininess associated with it. It is comprised of particles. Just like walking on the seashore, you will find sand and there are particles of sand. In fact, if you look at the Greek natural philosophers, especially Democritus uses the same analogy of comparing atoms to being made up of fine grains, like the seashore is made up of grains of sand. In fact, it was Democritus who first used the word atom, which is really a combination of A and TOM. So, do you know what this word means? Something that cannot be destroyed, indivisible, undistinguishable. In fact, there's a close connection between Sanskrit language and the Greek language. So in Sanskrit they have the word alif or a, which represents negation. So you have amar, jo mar nahi sakta. ठीक है, अमिट जो मिट नहीं सकता. So this is the origin of the word atom, in fact. And we've come a long way since the times of Democritus and Leucippus. Today we know that the atom is not an elementary particle. And we know that matter is made up of particles and it has a particulate or a corpuscular existence. But the atom is not the fundamental unit. That is why at the turn of the 20th century, when the atom was broken apart, which means people started looking at what's inside the atom, the subatomic world opened up. And it brought many new surprises. Lots of Nobel Prizes were given for those discoveries in which the atom was shown to be destructible. That is, being comprised of something more fundamental, other elementary particles. Becquerel got the Nobel Prize for radioactivity. Röntgen for X-rays, Thompson for the discovery of electrons, Rutherford, Chadwick. There's a whole list of scientists who actually prized open the subatomic world, that the atom is destructible. The atom is made up of something more fundamental. So, but the idea of quantization also started at the turn of the 20th century with Max Planck. So there was a long series of experiments that were performed even before quantum theory was born, which showed that matter is discretized or quantized. We've already looked at the quantization of energy, but matter is also quantized, which means that matter is made up of discrete particles, discrete units. And some of these units are fundamental, which means they cannot be broken down any further. For example, an electron, according to our current knowledge of physics, is a fundamental particle. It's an elementary particle. It cannot be broken down into anything simpler. But a proton can be broken down into quarks. A neutron can be broken down into quarks. A neutrino cannot be broken down into something more elementary. So there is a whole cornucopia, a whole encyclopedia of particles that are available. But matter on its fundamental scale is made up of these particles. And when we use the word particle, it conjures in our mind an idea of what does this word represent as an idea? What do you think of when you use the word particle?
Defined in space.
Right. Something that is defined in space, that exists somewhere. That's the best definition the best idea that encapsulates the meaning of the word particle. Something that exists somewhere in space. ठीक है, जब हम पार्टिकल का लफ्ज़ इस्तेमाल करते हैं तो इससे ये मफ़हूम हासिल करते हैं कि something that exists somewhere in space and of course in time as well. So, but the idea that of discretized matter or quantized matter is very old, as I've mentioned. A very important experiment was performed in around 1833 by the experimental prodigy Michael Faraday. In fact, remember that physics, like all other natural sciences, is an experimental science. So it is experiment that gives rise to an idea in most cases. And this is how the quantum theory was born. In fact, people were doing spectroscopy since the times of Lyman, Balmer, Paschen, Brackett, Pfund, Rydberg. All of these were spectroscopists. They were looking at emissions from various stars, from various elements. For example, you've done salt analysis, you put a salt on a flame, it gives distinct colors. You've seen fireworks, you see red fireworks, green fireworks, you see mercury lamps, you see these distinctive colors. So all of this spectroscopy was being done before quantum theory was born. And we've seen demonstrations in the classroom that show that these colors, these wavelengths arise out of quantized energy levels. So experiments were being done before quantum theory was born, and people were trying to understand or interpret these experimental results. And it was all of these experiments combined together that gave birth to the idea, to the theory of quantum mechanics. Alright? So experiments were on the driving seat in quantum theory, and the theory was on the back seat. Just like thermodynamics, James Watt had invented the steam engine, but thermodynamics had not yet been given birth to. Kelvin was performing his experiments, Joule was performing his experiments, but thermodynamics and statistical mechanics came much later. Likewise, communications. In 1887, Heinrich Hertz discovered radio waves. He transmitted a radio signal between 2 points. But the theory of communication and the theory of information theory was born in the 1940s by Shannon. So these are 2 or 3 very important and potent examples in which experiments were on the driving seat and theory was sitting on the back seat. So this is the history of science. This is how physics has developed. But nowadays, there are many ideas in which theory is on the driving seat. An experiment is sitting on the back seat. Rather, experiments are sitting in the boot of the car. डिक्की में बैठे हुए experiments. हो ही नहीं सकते experiments. मतलब string theory है. It's a theory. But it's very hard, almost impossible, practically infeasible to design experiments that test the string theory. So there are sometimes it happens in the history of physics that experiment drives the way, and sometimes it happens that theory drives the way. But in quantum theory, most of the ideas were being experimentally verified before an interpretation was found. So the theory was lagging the experiments. So in 1833, Faraday performed an experiment which everyone knows. You've seen in chemistry already many times. It's the electrolysis experiment. So for example, in electrolysis, if you have a bath of, say, molten sodium chloride, and you have two electrodes. One of the electrodes is a lump of sodium, and this is some other electrode, for example platinum, and you connect a power supply between these electrodes. So what would happen? The sodium ions would go into the solution, and there are already sodium ions in the solution. It's in fact molten sodium chloride. So these sodium ions will absorb an electron. Each of these will absorb an electron and make native sodium element, and it will deposit on the cathode. So this is called electroplating, in which this sodium, which could be impure, deposits itself in pure form on this electrode. Right? So what Faraday observed, he was measuring the current with a galvanometer. Faraday was very good in electricity and magnetism. You know the Faraday's law, you know the Ampere's law. He could measure currents. In fact, he was performing experiments with frog muscle, in which he twitched the frog muscle by applying what is called an action potential, and the muscle twitches because there are neurons in the muscle. So he is very good at experiments of this kind. So he could measure the time and the current using a galvanometer during the course of this experiment. And if you multiply the time with the current, you get the charge. So depending upon the charge, which means depending upon the product of the current and the time, he saw a relationship between the amount of the sodium deposited on platinum with charge. It depends upon the charge. So whenever there is 96,500 coulombs of charge that flows through this circuit, 1 mole of sodium, which is 23 grams of sodium, is deposited. And in fact, if he were a better chemist, he could have even measured the mass of the chlorine gas that is produced at the other electrode. Lavoisier, the French chemist, was very good at experiments of this kind. However, if instead of sodium chloride one uses molten barium chloride, then the same amount of charge would produce how many moles of barium? Half moles of barium. So this shows that the charge itself, which is flowing through the circuit, is discretized. It has a direct relationship with the mass. So mass contains charge, and since we have discrete units of mass, charge must also be in discrete units. So this was the first idea which led to the idea of the quantization of charge. That charge can only occur in discrete units. Because matter is discrete, so charge must also be discrete. So the electron had not yet been discovered. Remember, this is 1833. The electron had not yet been discovered. So Faraday gave birth to the idea that charge can be quantized. And we had to wait another 60 years before the electron could actually be discovered. So 1896 marks a very important year in physics. 1896 is when Becquerel discovered radioactivity. As far as I remember, the first Nobel Prize in physics was given to Becquerel for his discovery of radioactivity. And in the same year, it was the British physicist J.J. Thompson who actually discovered a particle, and he called it the electron. The electron is in fact an old word. Electron is the Greek word for amber, which is a kind of wood. And it charges when you rub it with some cloth like linen. So electron was the name given by Greeks to that wood. Because once you rub it with linen and then it can attract other smaller objects. So J.J. Thompson is credited with the discovery of the electron. And he measured what is called the charge to mass ratio of the electron. So the idea of the electron existing as a particle was born. ये एक पार्टिकल है और इसका कोई चार्ज टू मास रेशियो भी है. ठीक है. He did not independently find the charge on an electron or the mass of the electron. It was in 1911 that Millikan, the American physicist, measured the charge of an electron in a famous experiment called the oil drop experiment. You've seen that? Yeah. So from that the mass of the electron could be deduced. It was remember, these are very painstaking experiments because they take long. They require a lot of patience. A theorist would normally sit in an armchair in the comfort and cozy environment of his room. But an experimentalist really has to break his back in order to do these careful experiments. And you need students who can spend 24 hours at stretch working on these experiments. So physics was born in these laboratories, not in the armchair. But now the trend is shifting. Physics is moving more towards the armchair. So Thompson's experiment, and another very interesting point in the history of physics is, although J.J. Thompson discovered that the electron is a particle, it has a charge to mass ratio, his own son G.P. Thompson showed that no, the electron is not a particle, it's a wave. So there is a conflict between father and son here. And in the next week or so I'm going to talk about this conflict. What the electron really is. And we've already seen the electron diffraction experiment. Remember the very first lecture? So we have to make connection to the very first lecture in the next week as well. And try to consolidate the ideas of what is a wave, what is a particle. But all of us know most of us know what the Thompson's experiment was all about. It's just a cathode ray tube. And you have some filament through which a current flows, a normal arrangement. You have electrodes. This is positively charged with respect to this electrode. And this is positively charged with respect to this point. So electrons are emitted from the filament by thermionic emission, and they deflect and they move in the direction of in this direction. And if there are plates in between, like vertical deflection plates. So if this becomes positively charged, an electric field is produced, and as these elusive particles flow in the region between these deflection plates, these particles turn, the trajectory moves, they fall onto the screen, which is coated with a special material, a phosphor material like zinc sulfide, and it gives a visible signal, a phosphorescent signal. And you can see where the spot is hitting on the screen. G.
So So the battery shouldn't be the other one?
This is positively charged, so it's attracting electrons. So now if you look at this arrangement, if the length of these deflection plates is L and the distance between these deflection plates is D, in this region the electrons have a certain velocity. And what is the direction of this velocity? Towards the positive plate, but it's also moving in the straight direction, so it's a resultant. It has a Vy component and a Vx component, and there is an angle. This is the resultant velocity and there's an angle theta. Could you tell me whether Vx will be constant or not? Vx will be constant. And what about Vy? It's going to change because there is an acceleration. Can you find out what Vy is when the electron reaches the end of the plates? What is it? Please write on your notebooks what's the value of Vy at this point. There is no
value of Vy at that point because there is no deflection at that point.
No, but the top plate is positively charged, so the electron must be moving in the upward direction. There must be something that makes it go up. ये कैसे है? देखो, law of motion use करो कोई, equation of motion. Final velocity depends on initial velocity, acceleration, time.
इसमें forces नहीं करेंगे?
Force का
तो ये electric field लगेगी और उसका mass नीचे लगेगा.
Forget about gravity here. हाँ, तो बताओ क्या होगा Vy? It's just a simple application of an equation of motion. You studied in A levels. Call it E. Over?
CM.
What is CM?
So I use C charge, force of a charge, electric field.
Which is E, okay. Now, I would expect that you should be able to do this, in fact. If you don't, I'll be surprised a little bit. And what is T?
Time.
And what is time? Can you find out what the time is?
Electric field strength, charge, mass.
शाबाश. वो टाइम को भी आगे कर सकते हो. So Vy is acceleration times time. It's an equation of motion. The initial y velocity here is 0 because the electron is moving horizontally. So the acceleration is force over mass. Force is the charge on an electron, the electric field over mass times time. And what is the time it takes to go from here to here? It's this distance L divided by Vx. It's very easy. It's very simple. So this is Vy. Please explain it. Okay. I'm going to show you a demonstration of this on Tuesday. So this is a positively charged plate. A negatively charged plate at the bottom. An electron comes in, it's negatively charged, it's coming in with a certain velocity because this potential V0 has accelerated the electron to a certain energy, which is V0 times E. So V0 times E is the kinetic energy of the electron when it reaches this point. And will it have any Y component? No. It's just going to have an X component. So this is half mvx squared. So now when the electron enters this electric field region, the electric field is pointing downwards. So there is an upward force on the electron. It's being attracted to the plate. So it will deflect in a parabola in the upward direction. And why it will not go straight up? Because it has a horizontal component to its velocity as well. It has a horizontal component and a vertical component to the velocity adds up. There is a force in the upward direction, there has to be an acceleration in the upward direction. And we know that the acceleration, the final velocity is the initial velocity plus at. So you can write two equations, one for the x motion and one for the y motion. For the y motion, this is 0 at the start. So v at this point, the velocity has two components. It has a vy and it has a vx. And the resultant velocity is like this. So it's going to move like this in this direction, and it's going to hit the screen, and this angle is theta, such that tangent of theta is vy over vx. It's very simple geometry, very simple mechanics, nothing else. Now this vx, would it be the same as the vx of the electron here? Yes, because there is no acceleration in this direction. The voltages have gone off. This is a voltage free region in the x direction. So the electron will maintain its Vx, but its Vy is going to increase according to this formula. The more the time it spends in between these plates, the higher will be the vertical velocity when it discharges from the plates. Okay? And this time actually depends upon the x velocity and the length of these plates. So this time is simply L over Vx. So now we have a relationship between Vy and Vx. So this tangent of theta is Vy over Vx, which is equal to E capital E L over m Vx squared. So what Thompson wanted to find was this ratio, charge over mass. In fact, किसी भी पार्टिकल को आइडेंटिफाई करने के लिए उसका चार्ज ओवर मास रेशियो इस्तेमाल होती है. इसी तरह नए पार्टिकल्स डिस्कवर होते हैं. बोसॉन्स, न्यूट्रिनोज, ओमेगा पार्टिकल्स, all new particles in particle physics are discovered by finding the charge to mass ratio in most cases. So Thompson wanted to find the charge to mass ratio of these particles. So if this theta is small, which means that this length is small, then there will not be much deflection of the electron beam and the beam will be very close to the center, in other words, or this voltage is small. Right? So theta will be small when this voltage is small, or when the length of these plates is small, or when the distance between these plates is large so that the electric field is small. There are different ways of making theta small. And in Thompson's experiment, the actual experiment is now placed in a museum, in fact, theta was really small. So when theta is small, tan theta becomes almost theta. So theta can be measured. If you have this screen, you know this length. Thompson made his tube himself, so he knew this length. He fabricated it himself, so he must have known this length. And if you know this distance, let's call it y, you can find out what theta is. So you can measure theta. Thompson measured theta. So if you rearrange this equation a little bit, the charge to mass ratio becomes theta Vx squared over E over L. Now theta can be measured, L can be measured because Thompson made his tube himself. He fabricated it, so he must have known the length of the deflection plates. The electric field, how can one find the electric field? By the voltage between these plates and the distance. So this becomes equal to theta Vx squared E, the distance between the plates, the voltage, and L. Remember, this is not the accelerating voltage V0 that I've shown. Now everything is measurable. Theta is measurable, D, V and L. What about Vx squared? It's not easy to measure Vx. How would Thompson have any apparatus in the world that could measure the velocity of the electron in the x direction? He couldn't. So there is a problem here. Now a clever physicist, a clever experimentalist thinks that now there's a problem. How do I solve this problem? So what Thompson argued is, all right, so what he argued, I would like to find out the value of Vx. I can't measure it directly, so I must have some indirect means. Could anyone think of what Thompson could have thought? Could you put yourself in Thompson's feet and think of a way which is accessible to an experimentalist, a way of measuring Vx? Any ideas? Raise your hands. आप बताएं. Exactly, and that is what Thompson. आपका भी यही जवाब था.
Thinking more about finding the kinetic energy somehow, and then using the velocity from that.
But one possibility is to find the kinetic energy. This gentleman has mentioned that one can find the kinetic energy by, but in order to find the kinetic energy, an easy way could have been to measure V0 and E. V0 is known. This is what Thompson applied. You can measure it with a voltmeter. But the problem is he doesn't know the charge on an electron. So finding the energy is not easy. So the only possibility that comes to, there are two possibilities. If Thompson lived in 2013, he could have also used velocity selectors. But he didn't live in 2013. He was performing this experiment in 1896. तो उसके पास यही तरीका रह गया था कि एक मैग्नेटिक फील्ड लो, एक मैग्नेट लो जिसकी मैग्नेटिक फील्ड नोन है, and apply a magnetic field transverse to this direction. That is, apply a magnetic field into the plane of the blackboard, perpendicular to this. The electric field is downwards, so let's apply a magnetic field in this direction, which means you place, if I draw this figure in another way, you would have your electron tube. The electron is moving in this direction. These are the deflection plates. And then you take, for example, a horseshoe magnet. For example, a horseshoe magnet such that this is the north pole and the south pole is at the back. So the magnetic field is pointing inwards. And if I draw this, superimpose the magnetic field on top of this, the field is pointing in the inward direction. North pole is here, south pole is at the other end of the blackboard. So the field is represented by these cross signs into the plane of the blackboard. So what you really have are crossed electric and magnetic fields. Crossed E and B fields. Now could you tell me what will be the direction of the force due to the magnetic field alone? It's going to be downwards. Apply the right hand rule. The velocity is in the forward direction. Magnetic field into the plane of the paper, your thumb is pointing up, but these are negatively charged particles, so the force is actually pointing in the downward direction. So now you have a scenario in which there is an electric field in the upward direction, Fe, and there is a magnetic field in the downward direction, Fm. And if the strength of the field is adjusted such that the electric field becomes equal to the magnetic field, what is the direction of the resultant force? Zero. There is no resultant force. It becomes zero. So this spot can be steered back to here if the magnetic field is adjusted. So now how can one experimentally adjust a magnetic field? You have a magnet, how can you adjust its field? Use an electromagnet. So you pass current through the coils of the electromagnet, adjust the current so that the field strength increases or decreases, or change the spacing between the poles. That's also going to change the magnetic field. We can also change the voltage applied, but if the voltage is zero, there is no electric field, so Vy will be zero. You will not be able to calculate E over M.
No, we could decrease the voltage or increase the voltage to match that of the magnetic field.
We could do it either way. We could do it either way. In fact, this is how Thompson had done it. He used permanent magnet pole pieces. They were permanent magnets, they were not electromagnets, and he adjusted the electric field. It was a very strong magnet. He adjusted the electric field such that so strong magnet, the spot had come down. Now you adjust the electric field such that the spot comes back to the center. That's how Thompson actually did it.
You could have increased the distance between the magnets as well.
Well, that's generally not very practically possible. Because you have a horseshoe magnet, you can't change the distance between the poles. It's generally not an easy thing to do. So in this condition, can you tell me what the magnetic field will be? What is the magnetic field, Fm? It's EVB. And which V? Vx or Vy? Is it Vy or Vx? It's not Vy, it's Vx. Because Vy is parallel to the, it will not affect Vy. So you have to, the force is in the downward direction, okay, and Vx is parallel to the force. So Vy is parallel to the force. So you put